In today's lesson, we are going to learn about methods of proof. This is in the syllabus for section 1.6, just so you know, it has nothing to do with the textbook number. So what we're going to look at is we're going to look at how do we prove identities, and then also looking at the difference between this equal sign and the identity symbol. So to begin with, we're just going to look at a fractional equation. So in this first one, we have 1/4 plus 1/12, well, that equals 1/3. Well, how do we know that? What do we have to do? So if you remember back way long ago, in order to add fractions, we multiply by a form of 1. So I multiply 1/4 by 3/3, and that gives me, therefore, 3/12, right? Aren't those equivalent, 3/12 and 1/4? But then I have to add that 1/12 still to have an equivalency. So now I have two expressions that are equivalent to each other, hence the equal sign. But then what I can do is I can take those two and add them together, which gives me 4/12. But we wouldn't leave it as 4/12. What we then do is we take 4/12 and we simplify it to be 1/3. So what we did is we took this original equation, it's a true statement, and we just showed all of our work to get there. And then we have more true statements within there. What we can do with this is we can generalize this problem. So back to the next page. When we generalize, we put variables in, and then we make sure that they're true statements. So if I let 3 be m. So instead of 3, we put an m there. Now I have to make a statement that's true in this problem, and I'm going to have to change up my 4 and my 12. And there's a few different ways to do this, but what we're going to look at is we're going to go from an equation to an identity, where it's true for every single case, no matter what m is. So therefore, instead of 3, we have an m. Well, what's 4? That's just one more than 3, so that's m plus 1. And how do I get 12? Again, there's a lot of different ways to get 12 if m is 3, but the easy way with just using m would be m squared plus m. Okay, again, plug that 3 in, see if it works. It does. So now what I can do is I can plug in another value of m, like 2. I can plug in 1. Real quickly, if I put a 1 in there, I get 1/2 plus 1 over, so 1 plus 1 is 2, and that equals 1 over 1. So that's a true statement by plugging in another value for m. Again, what we're looking at is we're making a generalized statement. And that general result is what's called an identity. The identity emphasizes that it holds true for any real number m. So no matter what number I put in for each of these m's, it's a true statement. And if that's the case, we use these 3 lines. That 3 lines, again, deals with the fact that it's an identity. It is absolutely a true statement if you put an equal sign in there. Please know that. So this one here is perfectly acceptable. This one just says I'm extra special because this is an identity. It's a true statement no matter what real number you substitute in for m. Here's another example of a relation. 3x equals 6. So all we did here, if you notice, going from here to here, so looking at these two, so going from this first one to the second one of these is a relation. Which one is it? Again, a relation is when or an identity, excuse me, is what I meant to say. An identity is when the left side equals the right side no matter what you plug in. Is that true for this first one? Can I put any value of x in and get this out? No. How about the second one? Can I put any value I want in for x and get the second one out? Absolutely. And some of you might go, well, why do we have these parentheses there? Anyone think that? What does that mean? What operation? Multiplication, right? I can rewrite this and I get 2x plus 6. Look at that. It's exactly the same thing as that side. That's why it's an identity. They end up equaling each other with the x's on both sides. So what we're now going to do is we're going to prove these identities. So now that we know what identities are and how they come about, we are going to prove them. And there are 3 different methods we are going to use to prove them. We're going to use the left-hand side to the right-hand side. What that means is I'm going to take my left-hand side and I'm going to make it look like my right-hand side. So be careful so you know which one to do, because we're also going to do right-hand side to left-hand side. So we're going to take the left-hand side and move it to the right-hand side, and we're going to do this identity. So what I recommend that you do, you go through and you show all your work. So now what we're going to be looking at here is this is the identity. The next step that we're going to do is we're going to write equals or equations along the way just to keep our notation consistent. So I know that I'm going to take AB cubed and I'm going to simplify that out. So that is equivalent to A plus B times A plus B times A plus B, or which is the same thing as A plus B squared times A plus B. A lot of you know this shortcut. Square the first, square the last, multiply the two and double. And now this has to get multiplied by A plus B. So now I expand this through. So go ahead and pause me and finish this up. And when I combine all my like terms on the right-hand side, I get A cubed plus A squared B, so 3 A squared B's, 2 AB squareds, 1 AB squared, so 3 AB squareds plus B cubed. So what I just did is I showed that my left-hand side is equivalent to my right-hand side. So this was the identity, hence the 3 markers. So no matter what values I substitute in for A and B, the right-hand side is always the left-hand side. And again, you have to end up with that right-hand side here in the bottom of the proof. Okay, next one. We're going to now do right-hand side to left-hand side. So what I'm going to have to do is I'm going to rewrite this right-hand side to make it look like my left-hand side. So this gets a little goofy with how you represent it, because we usually start with what we have, and we do the work from there. Okay, so now when I go ahead and expand this out, I get x cubed plus 3x squared plus 9x minus 3x squared minus 9x minus 27. And I rewrite this and I get x cubed, that's 0x squared, 0x minus 27. That works as well. I now proved it equals my left-hand side. So I started with the right, I did my work, I got the left. Okay. Always write this statement out, this equation out, because we're not trying to do anything with this. We just want our end result to be here. So we're going to kind of ignore that that's even our one side, and we're just going to work with this one. And this one is our last method. This is where we're working both the left-hand side and the right-hand side to get something that's equivalent. So we're going to get something completely different that neither of them had. So what you end up doing is you work each of them separately. So therefore, we start with the 2a plus b squared minus 4a squared minus 2b squared. And then we're going to write out what this becomes. So I can start with squaring this. So this becomes 4a squared plus 4ab plus b squared. If you don't like doing the shortcut with the squaring, just write both of them out and go through the process. And then we have still the minus 4a squared from here, and then minus the b squared from here. So again, this is just an equation. I took the left-hand side and I'm rewriting it, and I'm simplifying it along the way. Now, sometimes when you do this, you might end up getting something that you have on this right-hand side. But if not, you just keep going until you get to a point, and then you're going to work the other side. So now I have 4a squared and a negative 4a squared, so that goes away. I have a b squared and a negative b squared, so that goes away. Therefore, this just simplifies out to 4ab. So that is what my left-hand side looked like. Now I need to work with my right-hand side. So my right-hand side, go this way a little bit, a plus b squared minus a minus b squared equal. I know I'm going to need more space. So when I write that out, I get a squared plus 2ab plus b squared minus, be careful. So I'm subtracting this whole thing. So it's a squared minus 2ab plus b squared. And I'm subtracting all of that. So I'll write another step. Be careful with those subtractions so you send it through. Okay, now we find our like part. So an a squared and negative a squared is 0. A b squared and negative b squared is 0. So 2ab and a 2ab makes 4ab. Therefore, we have proven it. And we know that our left-hand side equals our right-hand side because the left-hand side was 4ab, then the right-hand side was also 4ab. that's a way to work both sides until you get the same thing. So again, what you did is you proved this identity for all real numbers. So we're going to go back to the very first one that we generalized and prove this identity is true. So what we're going to do is we're going to either do a left-hand side to right-hand side or a right-hand side to left-hand side. If you notice, the left-hand side is the messy side, and a lot of times that's what you're going to start with. If they don't tell you which way to go, start with the one that's the most challenging. And part of this is just rewriting and using your Algebra 2 skills. So if I need to get these into a single fraction, I probably want to get common denominators. In order to get common denominators, I'm going to factor this denominator to see what this one needs. So I'm going to factor out that greatest common factor. So now what I have here, so let's technically do this right. And I was getting sloppy with my proof here. So we started with this one. So this is the left-hand side. That's what we're starting with. This is the left-hand side. And we're just rewriting it. So I factored this, and now I can see this fraction needs a factor of m. So now we have common denominators, so we can do what the numerator says, and we can rewrite our common denominator. Now, unfortunately, what I can now do is I can simplify, and I have a form of 1 here. So what's left on the top, and here's the bottom. This should look familiar. We do problems very similar to this in Algebra 2. So what we just did is we proved this identity. We proved that the left-hand side equals the right-hand side. So I took my left-hand side, I did some algebraic manipulation, I got true statement, 1 over m. Now, you have to remember that m cannot be 0 or -1 for this to be a true identity. You don't necessarily see it in the bottom here that it can't be -1, but you could see it up top. So this is how we prove identities using algebra, and this is an algebraic proof that we're working through. In this problem, I'm not going to do the whole problem. But in this problem, if I just gave you the option, what side would you like to move? Would you like to make sure that the left-hand side equals the right-hand side, or would you rather choose to make the right-hand side equal the left-hand side? You can legitimately do either one. If you know how to complete the square, you can show that this side is equivalent to this side. Okay. Easier, most likely, would be to show that this is equivalent to this by expanding it out, combining like terms. So that's part of what the process is. Sometimes is figuring out which way does make sense to do it from the very beginning. And that's about as far as we're going to go on that problem. But the last problem that I want to look at is we can use the fact that this is an identity. So see how there's the 3 marks here. What we can do is we can use the fact that it's an identity to figure out what A and B are. So now we're not proving anything, we're just solving. So if I know that this is equivalent to this, I can then solve for A and B by doing some manipulation. So again, you probably don't want to start with this. You want to start with this side here. So if I'm going to start with this side here, I'm going to expand out the square. So that gives me x squared minus 2xa plus a squared. And then it says plus b. So all I did is I took this and I rewrote it here. Again, this is not a proof, but we're using the idea of identities to solve for variables. The left-hand side was this. So now what I need to do is I need to set equal parts equal to each other. So x squared is equivalent to x squared. Now I find my x term. This is -6x. So where's my x term here? Right here, -2xa. Which means, and there's no other x's here, that means -6x has to equal -2xa. So now I can go through and solve for a. Divide both sides by -2x. A therefore is +3. I still have one more variable. They wanted me to solve for b. So since they want me to solve for b, this is my constant term. Neither of these have x's, which means that's my constant term as well. So now I can set equal the 14 to the a squared plus b. Again, all we're doing is we're finding like pieces on each side of my equal sign. Now over here, I already found that a was 3. If I didn't know that, I wouldn't be able to finish this problem. But since I knew that a was 3, I substitute that in. So I get 14 equals 3 squared, so 9 plus b. Subtract the 9 over. B, therefore, is 5. So in this problem, it is equivalent to x minus 3 squared plus 5. So that's how we can use identities to then continue to solve problems, which is a lot of what we'll work on in IB, is solving for individual letters along the way. So now you're going to practice proving, making sure that you keep track of left-hand side versus right-hand side. So again, right-hand side to left-hand side means I'm taking this and I'm manipulating it, and I'm forcing it to look like the left-hand side. And then over here, we wanted to go from the left to the right, so I'm manipulating my left-hand side to make it look like my right-hand side. And then the last one that we did was going both directions. So I rewrote both of them to solve. Those are our algebraic proofs we're going to look at in IB Math.